So
So
first speaker
didn't show up.
presentation is titled Lattice Boltzmann for Wave to Model Acoustic Manipulation by Mr. Esteban Castro Avila.
Yeah.
Please.
Just a second, and I'll start Zoom.
So let me know when you're going to start. If I can start now. Okay. Okay. Okay, so good afternoon, everyone. Welcome to my talk about lattice Boltzmann modeling for acoustic manipulation. So this is a brief summary of my master project that was led by Professor Paulo Malgaretti, Professor James Hartin, and Professor Jose Daniel Munoz Castaño. He is, by the way, he is with us. And welcome, and of course, we are going to start right now. So acoustic manipulation is basically the manipulation of objects and also particle droplets or even animals by using waves, but currently sound waves instead of electromagnetic waves. I don't know why it's not, I don't know, it's not working for some reason. Okay, there we go. Okay, so just for the motivation, these are the restrict. Okay, so we had, as I was telling you, it's possible to manipulate objects with sound as well as you can do it with electromagnetic waves. For example, the laser tweezers or laser or acoustic optic tweezers that was discovered by Ash in the 1917, and which was again then he won the 2018 Nobel Prize. So in analogous, you have also acoustic tweezering. So in order to manipulate objects or animals, for example, in this talk, for example, you can also set up devices, for example, parabolic manipulators. So you can just manipulate droplets, you can manipulate objects, microscopic quants, and the applications are basically, for example, non-invasive surgery. This is a recent study where they were extracting urinary stones from a pig, and it was a success using basically this kind of devices. And there is also an inspiring project that was developed here in the ATH in Zurich that they were developing a way to transport microrotors, which are beds coupled like a chain form, and that they can rotate with an external magnetic field. So it's an interesting project where we just inspired to make this project. This is what we are going to show you now. So basically, the physical relevant parameters is the following. So in this, most of experiments, not all, but most of them, we are in the microscale. So basically, we are manipulating particles of the size of 10 micrometers around, of course, or even 10s or 20 or 30 micrometers. Yeah, that's the typical size of these particles. Also, we are the sound, or the frequency sound of that sound is around 1 megahertz, which gives, for water, gives a wavelength of 500 micrometers, just as you can see here. So it means that for water, for example, we can compute something which is the skin depth, which is a thickness, delta thickness here that regard with the viscosity. And this is a parameter done to see if we can neglect or not the viscosity in this experiment. So it turns out that the layer, and there is a boundary layer around the object, which where viscosity is important, right? If this layer is too small compared to the object, then we can neglect viscosity. And that's why we do so. So we are neglecting viscosity for the most of the theoretical model. And that's what had been done around the years. And yeah, so, and also just to point out, we were studying the density matched case, which means that the density of the particles and the density of the fluid are the same. Of course, does not come from most experiments, but this was a test in that case, in that particular scenario, just to keep in mind. And just to clarify, the Reynolds numbers is pretty small, it's around 10 to minus 3, and maximum velocity of the particles is like 1.6 micromillimeters per second. It's actually pretty, it's just fast enough, but of course, take in mind that the motion of the particles has a pretty much different time scale from the oscillation of the acoustic waves, just to keep that in mind. So, so this is the theoretical background. Of course, this was studied since the 30s, since the third decade of the last century by King et al. So King was developing this second order acoustic radiation force. In order to get is the following, is where you have the conservation laws for a fluid, let's say the mass conservation law, and also the Euler equation, because we have an inviscid fluid, and you are developing a perturbative expansion from the pressure and the velocity. So you have to basically decouple this to expand this pressure and this velocity, which are the relevant variables, physical variables, into first order contribution, into second order contributions. So the first order contributions, if you only keep that first order, you can get the waves equation, the linear waves equation we all know. And that's actually a PDE that is easy to solve. However, this force right here is the force that will manipulate the object we are interested with. And this force will, as due to this huge time scale difference, this only accounts for the time average. So we are computing the time average of this force. And this time average just at first order yields 0, because of course, P1 is an harmonical field. So instead, we need to develop a second order expansion. But unfortunately, this second order expansion depends on the first contributions. As you can see, this expression right here. So this is the second order pressure, which is the hydrostatic part of the tensor. And then you have this term, which is the advection part. And you can see this second order too. So if you plug in everything here, you can solve the waves equation, and even you can compute this acoustic radiation force using this expansion, maybe using only the first order acoustic terms. And that's what we have done. We're basically was computing this force in general here numerically. And when you solve the waves equation for one sphere that is basically too small, it's as small that is much more smaller to the wavelength, which in most cases in the experiments, one can get this solution, this analytical solution that it was computed by Gorkov in the 1962 for a 3D case, that's a sphere. But we also have an analogous 2D case that is an infinite cylinder. And in that case, there is a solution was computed by et al. In the 2004, which was proposed with the solution. So what we are doing is to compute this force using and solving this equation numerically with Lattice-Boltzmann. And we are comparing with the analytical solution, which is written here. Just to, this is the summary of what we have done. And of course, and keep in mind also that the object is compressible. That means that has a bulk modulus of that, and also has a speed, sound speed propagation along inside the object and outside in the surrounding fluid. So that's all. So this is our Lattice-Boltzmann model. So this is a simpler model than the fluids one. It's not the standard that we are used to. This was proposed by Chopard in the 97. It's basically that you make the classical discretization of space, and then you have these two macroscopic quantities, just as the same as fluids. Instead that you just have a momentum variable here that is a vector field, and which is actually different is this equilibrium distribution function. So it's most expanded up to first order because our equation is actually linear. So that's why in our BGK single relaxation time, we have to set this up. And of course, that might scare you because of course, when you in Lattice-Boltzmann, you never put this to a half. But as we are not dealing with viscosity, we don't need to associate any parameter with that. We can eventually do that. And in the Champanescope expansion, you can see that it's only necessary the mass conserving law, and the first order conserving law is basically transforming to a linear that if you combine them, you can get a diagonal tensor for the second order moment, and then you get a waves equation. That's why we set this to a half, and this always set to a half. So finally, we were using for the 2D case, we were using DTQ5. Of course, you can use another lattice that is more applicable, but this is just enough for our model. In the 3D case, we were using DTQ7. So the model that was proposed by Chopard was made in such a way that we have this kind of lattices with no diagonal vectors, but however, it should work for other cases so that you can, of course, you need to compute the weights properly to fulfill this property, which is written here. And that's all that's our model, basically. And so we were implementing this model into, and additionally, we need to compute the force, the acoustic radiation force that we're looking for. So how did we do that? So if you notice, this constant appeared in the equilibrium function, which is a tunable sound speed. So this is a parameter that you can tune, that you can change. And you can change also as function of space. So basically we were like mimicking an interface where the spherical region, so all outside we have one value, which is C0, and inside we have CP, which is inside the sphere. So that's the sound speed of the particle as well. And that's the function that we use. So this function basically makes a smooth interface in between those parameters, those values. So then you compute the lattice Boltzmann. Of course, those are the variables with the distribution functions. And after that, you interpolate them. So we make an interpolation over a coded mesh. So we are defining a mesh and we are coding up in the interface so that every marker, every vertex is gathering information interpolated of these macroscopic fields. And of course, this interpolation is made with this summation and with this kernel. Of course, this is not the only kernel you can use. You can use any other kernel, but this is the one we have used. So these are the numerical tests. So our first numerical test was done to compare between two implementations. We got one implementation for the 3D case and another implementation for the 2D case. And we were just comparing them to see that they were validated and that they are just solving the analytical case of a point source. Also, we were doing a standing wave propagation. So this is just how to generate a standing wave. And there is also, for example, when you modify the speed of sound in a flat interface, you have a refraction problem. And this refraction problem will just fulfill a boundary condition, and we were just ensuring that it's working. And finally, just for demonstration, just in the sake of demonstration, here is the same interface, but with modified in the spherical case. Yeah. So at the end, we developed a simulation. So just to clarify the parameters we have used. So we were using a domain of 250 times 64 cells in the 2D case and 250, 64 times 64 for the 3D case. Also, we're doing a variation of any parameter. So as we are in the density match case, we had to consider that the density on the surrounding fluid and the density of the particle are the same, just to simplification, and because the model doesn't contain any density that you can tune. So we can tune actually just the speed of sound, and we just define this factor, which is dependent only of the speed of sounds of both objects, of both the fluid and the object. And then we have these power relationships. We have R, we have this P8, which is the amplitude of the acoustic waves. We have K, which is the wave number of the acoustic oscillations. And we also have this dependence of the position, which is sine of 2kx, which is for both cases. So we were confirming this relationship, so measuring the force and then varying those parameters and ensuring that these relations are fulfilled. And the fixed parameters are taking these default values that you can see in this table. So that's what we have done. And for this first result, we can see the dependence on the position. So we were measuring the acoustic radiation force for any case where the particle was placed in many positions here, according to this graph. So this is the actual position of the center of the object. And then we were measuring all the acoustic radiation force, and we can see that clearly it satisfies this relationship in both cases, either 3D and 2D. These are our first results. Second result is regarding the dependence of the radius of the particle, the wave's amplitude, and the wave number. And here we have power laws for that. You can see here in the formulas, we got exponents is 3, 2, and 1, and we got 2, 2, and 1 in the 2D case. So basically, we were ensuring that our force is proportional to the cube of the radius, to the square of the amplitude, and is linear to the wave number. And as you can see, those are the errors. Those are the relative errors compared to the expected exponents for the linear fit. Just to clarify, when you are varying the wavelength, you want to ensure that yours have still a pretty small particle compared to the wavelength. So if you overcome this approximation, always you will have a discrepancy with the theory, because the theory considers that approximation. Of course, the simulation will differ a little bit from that if you are lowering the wavelength to a point when these are much less than lambda is away. So you have to keep in mind that. And finally, with proportionality with this factor psi, so the factor psi is basically what defined previously and is dependent of the relation within the sound velocities. So we are expecting that was linear, and eventually it is linear. So yeah, that's something that more additional comments on that is that the fit was basically 99% accurate. And just to summarize or to conclude, we have proposed a numerical methodology to compute the acoustic radiation force on a sphere, and we have compared with the analytical solutions, and this agreement is basically good. And we have used lattice-Boltzmann. We have used a simple model, which is the Chopard lattice-Boltzmann model for waves. This was a model that was proposed so many years ago, and we have shown that this is useful to compute this kind of things, which is a nonlinear phenomenon. As I told you, this is a second-order acoustic radiation force, and we managed to do so without having to solve Navier-Stokes equation, because Navier-Stokes equation is hard to solve. So how many times left? 1 minute? Okay, just basically to mention that the Navier-Stokes equation is usually hard to solve, even to deal with compressibility. So that's why this offers an alternative in order to compute for more small objects, and is general, not only for spheres, but you can do for another particle object. And yeah, that's all I can tell. So this project was not possible without them. Basically, these are my main supervisors. And also I would like to say thanks to the higher team, especially to them three, because they were the ones who helped me with the development, with all the support and all the acknowledgement to the academic advice. So yeah, and of course this was funded by BAILAT, which is a scholarship program, and for the University from Colombia. And that's all. So that's all I can say. So thank you very much for listening.
No, thank you very much for your interesting presentation.
Very clear to me how you compute the films by interpolating the value of using that expression. But since you have an object that is dynamically coupled to the medium, couldn't you get the force directly without any assumption about an expression?
Okay, so the interpolation was done in the following manner. So we have a set of Lagrangian markers, or let's say vertices, that were located. So at any lattice-Boltzmann step, you get this computation of the macroscopic quantities, right? So we after the collation process, we compute this, which is the updated quantities, and then we basically every time step you can get an interpolated value of it. I mean, you have a local position of the Lagrangian marker there, and the process between those is that basically we have to take the neighbor cells between that are around, and we have to compute the interpolation from them. And doing so, we develop this summation, and afterwards we can get an expression of an element in the integrand. So basically here we are computing for one single dot, one single vertex, and that's only for an element of a tiny surface element. And if we add them together, we will eventually get a value of the total force. So I don't, yes, just let me sure if I asked for the question properly.
I can't phrase. I was thinking, so these breakpoints,
Yeah.
they change dynamically in response to the fluid? Can the object deform?
Okay, that's an interesting question. Yeah, exactly. Yeah. Oh yeah, so this is actually not this is not an inverse boundary in the sense that the object, the mesh won't deform, is static into some sense. But as we, so what one should do is basically an inverse boundary method. Just not just to interpolate, but also to exchange this interpolation back to the lattice in order to get momentum conservation between the object and the lattice. That's what one should do. However, what we have done is to put a static, this sphere is static, not moved. So we are not actually doing that. And if you want to make a motion going on, so we are assuming that the time scale of the oscillations in the lattice Boltzmann is much smaller than the object. So not every time step, but every oscillation, which are thousands of time steps, we are updating that motion. Of course, in that sense, there is no conservation of momentum. There is no. But if we do so every thousand of time steps, maybe this error is not so important in our calculations. As soon as the object is able to move, of course. Okay.
The question is very good prediction or comparison of the force that you could do with the force of the theory. But the theory is for an infinite system, and you have a periodic system. So in a way, you have like an array of these objects. So I was surprised that there was no effect of a hydrodynamic interactions with the images of this.
Okay, yeah, I am surprised too about that because so what should happen here is that I think that this effect of making, I mean, there is an object here, but also here in the middle. That's what you think, and so this scattering should occur also for that. So why we are not seeing any effect on that? We actually have to be honest, we have not studied this effect. So, but if we want to do so, basically we want to vary this length, which is 64 for us. And as we are using 10 cells, this 5 and 5 here, maybe this effect is not so important, and that's why we didn't see. But if we were making a 10 cells size of the object, and our simulation size is 25, let's say, or maybe something less than 64, maybe we should see some effects on that. And it will be interesting to investigate how is the effect of the boundary conditions. And what one should do actually is this free condition, in the sense that one can copy the cells, and maybe at first order, it won't affect too much in that sense. But that's something we basically decide not to do so, and we're deciding that way. And well, the agreement was not affected at all. But yes, that's the one should do. Okay, thank you. Thank you very much. Thank you very much. Okay.
Should be. Oh, it should just be this. The arrow keys. Ah. Let's go slide. And the stick. The stick there. Okay, thank you very much. Okay. Hi everyone, my name is Jose Daniel Muñoz, and I am at the National University of Colombia in Bogota. So what I will show you is to use exactly the same model we saw in the last presentation to simulate the acoustic of an auditorium. So how it works, no? So we will review a little bit on auditorium acoustics. We will talk about the previous methods, so how this lattice Boltzmann for waves works for that, and then we'll use this method to simulate the reverberation times, the clarity and definition, and to simulate the frequency and time responses. So An auditorium, yeah, is intended to have to enhance the intensity of the sound by using some first reflections that come very close, no, in between 15 and 80 milliseconds. 50 milliseconds for the speech and 80 milliseconds for music. And thereafter, no, you will have multiple reflections who made a reverberation time here. And the idea is that with this should be large enough, no, to have some sense of warning, but not too much to disturb the sound. And it depends of the absorption coefficients on the walls. The absorption coefficient experimentally is usually measured with this experimental setup that is known as the Kunz tube. And then you have a standing wave, and just by measuring the maximal and the minimal amplitude, you can compute the standard wave ratio, and then from that, the absorption coefficient. And the reverberation time, that is one of the most important things, can be computed in different ways. This is the sound intensity in logarithmic scale, and usually you have something that goes like this, and then you change the exponent. If you use that one, yes, and you extrapolate, when you go to minus 10 decibels, and you extend that to minus 60 decibels, this is called the early the diffusion time. And then if you use minus 30 decibels and go to here, you have the reverberation time for 30 decibels. The theoretical one, the reference one, is the reverberation time for 60 decibels, but this one is very hard to measure and also hard to compute. So usually you use this one or that one. And if you have that these are not the same, yeah, you feel like this is dry, that this auditorium is dry. So the idea is that this one should be not so different to that one. What is the typical reverberation time for an auditorium? It depends. If you want that for speech, it should be somewhere between 0.4 and 1.2 seconds. And if you are looking for orchestral music, it will be between 1.2 and 1.6. And for organ music, let's say in church, you will need a larger one. There are two theories for that, very old ones. The first one is by Sabine, that gives this formula and this effective area. This is the volume and this is the area, and this effective area is just the weighted sum of all surfaces by the absorption coefficient. And this is a modification by AERO that was used before. This is very old stuff, no? This one is from the 30s. Okay. And finally, two other parameters are called clarity and definition. So if you have the acoustic pressure and you define some time, you can compare the total power before and after, and that is called clarity. Or if you compare the one before and divided by the total one, that is called definition. Okay. What were the methods before? Let's say a computer program, a commercial one like Odeon, use ray tracing. And ray tracing is really complicated. You start with a source, and the source is reflected by the walls. And then by reflecting by the walls, you will have a tree of other sources. So usually this goes like to the level 3, to level a tree to level 3. And then you have to cut all the branches that are not alone. This is the first part. And second, when you have a raw surface, you simulate the scattering by using multiple sources on that point. And you will use some angular intensity, and you can have to compute for the absorption coefficients on the walls and also for the absorption on the air. And this is how commercial software works. Okay, now let's try to do it by lattice Boltzmann for waves. So let's go for waves. You know what a lattice Boltzmann is, so I don't need to show you. But if you made a second order channel expansions, so the first two conservation laws you obtain are this one and that one. And if you use tau equals 1/2, this tensor here is just this one, no? Given by the first component in the perturbation expansion on the constant number. So if these are the two ones you have, the two equations you obtain when you use a LBGK. So how do you handle that to obtain the wave equation? It's very simple. If you find a way if you choose the equilibrium distribution function in such a way that this tensor is the diagonal tensor, then the divergence of this tensor is just the gradient of the term. And if you replace that here and takes the time derivative, you will obtain, if you take the divergence of that equation, so you will have the Laplacian here. And because of the first one, you will have the second time derivative of the density proportional to the Laplacian of the source, and then you will have waves. So this, how do you obtain that? Let's say that you have a velocity set with some weights in such a way that this second order tensor is diagonal. And what you need is a diagonal tensor. So if you compare both of them, which equilibrium function will you take? You need that this tensor is defined like this, and you have that property. So the first idea will be to take the equilibrium distribution just like the weight. If you take just, because it gives 1/4, you take 4 times that, and you will have 1 and 1, 0, 0. And if you multiply that by the pressure, that is c squared rho, so you will obtain that tensor. Thereafter, you add 2 other terms, one to assure that this will be verified, another one to verify that the sum of the equilibrium distributions gives the density. And then you have here the equilibrium distribution function for the diagonal tensor you want. So this is like a curve recipe. So you can do any diagonal tensor you want. Okay. And this makes waves. What about the absorption coefficients at the walls? No, it's very simple. We just are using bounce back, but multiplying by a factor. The larger the factor, the more reflection you have. So if this factor is 1, the absorption coefficient is 0. And if the absorbing factor is 0.9, the absorption coefficient is, if this is 0, the absorption coefficient is 0.9. Why not 1? Really, I don't know. No, but this is the way we verify that we can use this bounce back, yes, with a factor, to simulate the absorption coefficients on the walls, and it works. So we have everything to simulate an acoustic room. This is, for instance, we have, this is our source. This is the places we are measuring. And usually what you obtain when for the sound intensity is something like that. And this is the first part, that is the early reverberation time. And this is the final one. So this is our system, is 10 meters times 16 meters times 22 meters in size. Yes, these are the areas for the 10 walls we have. The source is here, and we are here at these 6 points. So which cell size we are using? Okay, it depends on the on the frequency, but let's say in this example, we are using a frequency of 150 hertz, that it goes to a wavelength of 186 centimeters. And we choose to use 5 centimeters boxes or 10 or 20 or 40 centimeter boxes. So you can see we are dividing such a huge space in boxes of 5 centimeters cubic, or 5 times 5 times 5. So you see that from 5 to 10 is more or less the same, no? This is here the early reverberation time, and this is the time to 30 decibels. So this is the one to 10 decibels, and this is the one computed by 30 decibels. And you see that from 10 to 5 is more or less the same, no? So this is the blue and the green ones. So let's say 10 centimeters, that corresponds to more or less to one divided by 14 is enough. No, it's very good. If you are forced, you can use also divided by 7, and it will be enough. So you need between 7 and 14 cells to resolve one wavelength, and then everything will be fine. Okay, let's remember the reverberation times. One simple test we can use is to set the same absorption coefficient to all the surfaces. In that case, the Sabine formula tells us that the reverberation time goes like 1 divided by the absorption coefficient, and that's what we obtain. Also with Odeon and with our method, and also it compares well with the theoretical expressions. And then we can compute, and then we are comparing the lattice Boltzmann simulations with the commercial Odeon program. And you see that, for instance, for the early reverberation time, so the one of minus 10 decibels, it works quite fine. No, our simulation is always below, no? And it is around 5 to 20% in some points. But just remember that here we are simulating the wave and not the sources, no? So it works fine. Yeah, it's not a perfect match, but it's okay. If we will look for clarity, we have more or less the same, and also for definition, we have more or less the same, yeah, with some differences, and these differences are not systematic. No, it depends on the frequency, and it depends on the absorption coefficients. And finally, we can look at the frequency response. So for this case, we use a superposition of frequencies all with the same amplitude as an input source. So equally distributed in frequency. So this is logarithmic. And this is the input, and that are the outputs at 5 different points, at that points. And this is what you obtain. But the way we use that is you put the source, yes, and then you measure the intensity at that point, and you wait until the intensity becomes to a steady state. And then you turn out the source, and then you look at the exponential decay in the sound intensity. But we can do another thing. We can simulate, we can compute for the actual sound response. So we can put a source here, whatever you want, and then we can hear what a person will hear here or there or there. So let me show you how it works. So I will use this microphone. I will not sing. No. So, but let's soprano singer sing. So this is the input. For instance, this is the input. And now let's hear the output when all walls are totally absorbing. So when you have no reflections. So it has some differences because you have reflections. Okay, you don't have any reflection, sorry. And then let's look with everything reflecting too much. Of course, this will be a bad auditorium. So let's look at something like 0.5. So a little better. So we can compute what a person actually will hear, yeah, in any place in the auditorium. So these are the conclusions. So the lattice-Boltzmann method for waves shows a promising alternative to simulated auditorium acoustics. No, reverberation times, clarity, and definition are around the 20%. Agreement with ray tracing algorithm. So which one is better, the ray tracing or the lattice-Boltzmann? Okay, we have to do experiments. No. We have performed some initial experiments, not in such a big room, but in a classroom, and it works more or less. But I didn't show them. But but we didn't compute that with Odeon. So this one I show you is the auditorium that you can use as without paying Odeon. No, that is the reason why we simulate that. But the method also allows to simulate the actual soundtrack a listener hears, and further work should be known to compare with experiment measurements, yeah, with both systems. So we have to buy Odeon now. So thank you very much. And okay, by the way, this was the undergraduate thesis from Daniel Jair James. Yeah, he was the one to make everything. And yeah, thank you for your attention. The lattice Boltzmann is quite fast because it was simulated on CUDA. So is for some simulation it takes 5 minutes. So the larger ones like that, the one we heard, it takes like half an hour. Yeah. Yes, of course, it's no problem at all. Yep. But you can combine different sources on. Yeah, it's not a problem. You can impose the fields as you want. Yeah. Okay. So let's say I don't have the number, but we can compute it. So it's like 10 times 16 times 22, no? It's like 10 meters, 20 centimeter, 5 centimeter size. So it'll be 200, no? It'll be 200 times 3,200 times no, sorry, something I did wrong. Okay, yeah. Just a second. So 2200 divided by 5 gives 440 times 160 divided by 5 times yes, is like 28 million cells. And each cell will have seven single precision or double precision. So it will be times 6 times 4, no, times 2. So let's say 1.3 gigabytes. Sorry? Yes, only one GPU is enough. Yeah.
Is there any, it's like you're quantizing again right? I mean, you're digitizing the signal of the lattice in a sense or not? I mean, do you have an interplay between the wavelength? No, but I guess the discretization is always much smaller than the wavelength, so is there
The discretization is between, you need between at least 1/7 of the wavelength. So, but it's better if you have 1 divided by 14. So 14 cells to resolve one wavelength. Yes, and then it works perfectly. Yeah, and of course, space and time are related, no? So here, at the end here, yeah, you need, this here cannot be negative. So this gives you a limit for the way, for the speed of sound. So usually you use 0.5. So the speed of sound will be 0.45 cells per click. And then it is stable. Yes?
Big question about this model, because you said that you do this expansion to first order, you have the wave equation, there is no dissipation, but this is an expansion. So I wonder what are the sources of dissipation? If you would really look at the propagation of a wave,
Yes.
eventually will dissipate.
Uh-huh.
If this can be quantified, so you can know when you will depart from the wave equation.
Okay. So the wave, what Esteban showed, no? The wave equation is obtained when you use first order perturbations. Yes, but here the wave equation is exact to up to second order. Yeah, and what is the difference? And here you are just simulating the wave equations. What about the actual air? In the actual air, you will have some absorption. Yeah, and the way you can simulate the absorption is just to use the same trick. So to multiply all the distribution functions by a factor at any time in any place inside the volume. And then you will have you can simulate the absorption you want. Yes.
Have you tried to do the simulation of a wave for periodic time and just measure how much it dissipates to see if you have numerical dissipation? Because again, this is an expansion.
Yes, that's true. Yes, you are right, and we didn't do that, but yes, we will have some dissipation, of course. Yes, I agree. Yeah. Because no, it's just the way it was defined in logarithm. No, this is not here. What I presenting is in decibels. No. So let's say this is. No, this is not negative. No, it's just this is not zero. This is not zero. Yeah. Here, and this is logarithm. So this means is this 1/10 of the initial intensity, and the intensity is proportional to the pressure to the square. So here is 1/10 of the initial intensity. This is 1,000th of the initial intensity, and this is 1,000,000. Yes, and the reference value for reverberation times is 1,000,000. So if you compute that here, you just multiply it, you just take twice the time you measure to give a value. So all reverberation times in acoustics are given at 1,000,000, no matter how do you compute it. So it is extrapolated, that's all. Yep.
Session, we have some, what? So.